Our last section is one that's definitely on every AP test, and that's the Beer-Lambert law. This is another form of analytical spectroscopy that we're going to use in class for our lab because it's such an essential part of any type of chemistry class. So this uses UV vis, and what this does is that the idea is that if we have a solution, we want to determine how much of that solution is in there. Generally, we would use molarity, but this is used when the amount of concentration in there is so small, doing quantitative molarity work isn't practical. So what we do is we originally get a solution that we're trying to analyze and find out over what wavelength does it seem to absorb the most of a substance. Most light. So in this case of this one example, absorbance is the idea of how much it absorbs of the light through the instrument itself. At this case, we looked at many different types and found out that this would be around 553 or so nanometers of light would actually give us the most absorbance. Now you might see these terms micromoles. That means times 10 to the 6th, times 10 to the 6th mole. So very, very small. And it makes sense that the more concentrated it is, the more it's going to be able to absorb. So what we would do is we would make this idea that the increase in concentration is going to be the amount of absorbance. And I say, okay, I'm kind of getting that. The more concentrated the substance is, the more light it's going to absorb. That makes sense, right? Something dilute is going to be easier to see through than something that's opaque or darker. What we can use, though, is use math in order to get this idea for what we have. So it looks more complicated. Again, we'll work through it through our lab. But the idea is that you have a constant value, this epsilon, length of the solution, which is generally 1 centimeter, and then the concentration, which is we think of as our molarity. We look at a logarithmic scale when it comes to this, and we'll be determining the concentration of food dye in a drink after you determine what's the best information to come to a linear conclusion. So we're having you explore a little bit with the UV vis to see what is the best relationship in order to get a linear function. Because once you have a linear function, you can easily determine the equation to that, and therefore be able to extrapolate any types of amounts based upon different types of solutions you have. Essentially making an unknown structure for determining a known structure, the equation of the line, for an unknown concentration that we're going to be testing. Now, there are some limitations, okay? So it's limited by chemical and instrumental factors. So reasons why you wouldn't get, or why you wouldn't get linearity, nonlinear, is you get deviations of these coefficients at high concentrations. You see a high concentration in this case is 1/100th of a molarity. Very tiny, because you get electrostatic interactions between molecules that are very close to each other. So you start having those intermolecular forces come into play, which can cause issues. You get scattering of light due to particulates in the matter sample. So if you have something that is considered chunky or cloudy, that can be a problem. You might have fluorescence or phosphorescence of the sample because you do have light going through it. It might absorb some of that energy and then release it, kind of releasing its own light, giving kind of a false value. Changes in refractive index of a higher concentration. So refractive index is how it bends light. And so if you have a higher concentration, it's going to bend light slightly differently, and that can be an area of getting incorrect data. Shifts in chemical equilibrium as a function of concentration. We haven't talked about chemical equilibrium. We talked about that, I think, unit 7. So the idea is that as things shift, you're going to have different amounts of it. So it's not consistent. So based upon temperature and other factors, you might have more or less than the actual amount of what you're trying to analyze. That can be, of course, a problem. As you increase concentration, it may get used up and lower than what you would expect. You get non-monochromatic radiation, so many different types of light. They can be utilized by going relatively flat parts, so getting a very narrow range of what you're trying to examine. And then, of course, stray light. You can't get rid of all the light around us. It's kind of in a little boxes you'll see to minimize the amount of light that gets in there from the surroundings. All right, so we're going to work on this some more when we do our lab, but this should give you an idea of what we're looking at and how this can actually be of use to us. All right, take care, and I'll talk to you later. Bye-bye.